measuring complex quantities. Complex quantities, of course, in the frequency domain mean phasors. So we measure amplitude and phase. We assume that everything is working or is harmonically time dependent. I have sine or cosine omega t with some phase and some magnitude. And equipment that are capable of measuring both amplitude and phase are vector. You say vector network analyzer. In order to distinguish between this equipment and scalar network analyzer. A scalar network analyzer measures just the magnitude. Okay? Of course, from the measurement point of view, anything which relies on the magnitude only is highly welcome, because you may use a very, very simple detector, which is rectifier, but fast rectifier composed of diode and capacitor, in order to follow the envelope. Okay, and in this case, things are much cheaper. But if you measure vectorially, of course you have to do many additional steps, which make equipment very, very expensive. Okay. Let me come back to the last equations we derived. We had the discrete Fourier transform Rm bar was R bar of omega m. It was given by summation from n equals 0 to n minus 1. We had here Rn e to the minus j twice n omega naught delta t times e to the minus j n m twice pi over n. You can correct me if you... This is the DFT. The IDFT is Rn is e to the plus j twice n omega naught delta t over n, and then here we have m equals 0 to n minus 1, Rm e to the plus j twice n, nm twice pi over n. Okay? The expressions are highly mathematical because you have n and you have delta t. Okay? Both are your choice. Actually, what you choose actually is n. You say, okay, usually you have 2 to the power something if you use a numerical algorithm. So say 1024 or 265 or something like that. Okay, and you know the entire length of your profile is n times delta t. Now you can think of the whole thing as, if I fix delta t, I know it, so I know the entire length. The other way around, and I can also change delta t, scale delta t. I take 1/10 of delta t, and I have the same number, so I will reduce the length. So everything is scalable in your hand. Okay, but let us come now to the relation which we put, which was twice delta t delta omega was twice pi over n. Was it so? Let us. Oh, it was so. In other words, you have delta omega times delta t is pi over n, which means that delta t, this is actually your space domain resolution. It is how to resolve different steps. It is given by pi over n delta omega. Now if you look, if this is omega naught plus delta omega until omega naught plus n minus 1 delta omega. N times delta omega is roughly the bandwidth. And omega is actually angular frequency. If you express it as real frequency, hertz, you will have, this is here, n times delta omega is twice pi times the bandwidth. So you have delta t is pi divided by twice pi times the bandwidth. So you can say it's something like 1 over twice b. So the wider you measure, the higher the resolution you can achieve. This is the first occasion we see the relation between resolution and bandwidth. Imagine now that you have two jumps, two interfaces within the same delta t. So we have, this is here, delta t, and we have maybe jump here and another jump here. Okay, so the separation between both, of course, it is as delay time or flight time, but we know now that we can very, very simply transform this in x, because different epsilon r's means different slowing down of the wave. So we have the same flight time, but if we slow down high epsilon r, the same time will correspond to smaller x, and the other way around. No, same time to a bigger x, and the other way around. So therefore, let me, within the framework of our approximation, we bring this here, and we bring this there. So we can't distinguish anymore. Much more worse is if you have both within just one half. You will collapse both at the same time. So you will not distinguish them anymore. So if the distance between two successive steps, two successive layers, or if the thickness of a layer, which gives rise to the distance or is equal to the distance between two successive interfaces, if it is slower, if it is smaller than delta t over 2, so in this case you will collapse the two on the same side. So this gives you the feeling of the resolution, and you may raise the resolution. I will discuss resolution in another occasion in terms of convolution and so on. But at least now, because we discretized everything, we work with discrete data. You know now that the higher the bandwidth, the better the resolution. Okay, this is one aspect. Physical equipment, they don't have unlimited bandwidth, because even if you decide, okay, if you have a generator, signal generator, which is capable of covering 10 giga, so you may think, okay, I have 10 giga bandwidth, so I will start my measurements from 1 giga to 11 giga, okay, and I can now calculate the resolution. I have the resolution in time is immediately here, times, so you have delta t is equal to 1 over twice b. So if you have, say, 10 giga, it is 10 to the power 10. So 1 over 10 to the power 10 is 0.1 nanosecond, right? 0.1 nanosecond. And if you consider this in conjunction with the speed of light, irrespective now of the slowing down due to epsilon r, but imagine that it is free space, so you can also calculate the corresponding delta x. So we can say delta t is delta x roughly divided by C naught, right? Because C naught delta T is delta X. And this is here is 1 over twice B. This means that delta X is C naught twice B. So let us have an example. If you have here, say, in millimeter, say 3 times 10 to the power 11 a millimeter, divided by 2 to the power 10. If you have 10 gigahertz, of course it is huge. So you have here something like 1.5 or 15 millimeter. Resolution. So just in order to have some feeling. Okay, I can distinguish between steps within 15 millimeter. Of course, 10 giga is really very, very high bandwidth, because let us come now to the instrumentation. Instrumentation means which equipment can give me such a huge bandwidth. Any measurement equipment has a finite bandwidth. Let us consider the vector network analyzer. In a vector network analyzer, you perform everything around the IF. Maybe in the last 10-20 years, they can digitize fast. You can work digitally in the baseband, because you may have now some samplers in the gigabit per second range. Okay, so that you can sample your signal, and you can, if you have a sine wave, you can know exactly the phase and the magnitude and so on. But otherwise, the bandwidth you can deal with is, say, with the most fast processors, is something like maximum of 2 giga. I don't think that you see something now much larger than 2 giga. But this is not only the problem, because this is only the digital signal processing. Much worse is, if I'm really measuring in the free space, I have antennas, because I produce the plane wave by generator, and this antenna has a bandwidth. Usually the fractional bandwidth plays the role, not the bandwidth itself. It is, you can say, you can have a system with, say, 10% fractional bandwidth, which means if your central frequency is 100 giga, so you may have 10 giga. But if your central frequency is 10, you may only have 1 giga. And as you see here, it is not omega naught. Omega naught here doesn't play any role. It is actually the bandwidth, n times delta omega, which dictates the resolution. Therefore, before just talking about nanometer resolution or something like that, you must take care. And because of the instrumentation, which means bandwidths are usually fractional, you can now imagine what is the advantage of terahertz as compared to millimeter wave, as compared to microwave. It is one. I will come to other factors now. So from the instrumentation point of view, your measurement equipment, as I told you, the fractional bandwidth. So if I'm working in terahertz, by the way, terahertz is, or submillimeter wave, it is not real tera, because the community describes everything between 100 giga to 1 tera as a terahertz range. But this is, in fact, it's better called submillimeter wave, the submillimeter wave. But 10% fractional bandwidth is common. So actually, it is not a big deal for those of you who deal with design and with manufacturing. You know that something like 10% is okay. So and almost all geometrical dimensions, almost all, are linearly scalable. So if you have an antenna of, say, diameter 1 meter, working at 1 gigahertz, it's completely equivalent to an antenna of diameter 10 centimeter working at 10 gigahertz. So 1/10 to 10 times. It's equivalent to 1 centimeter working at 100 gigahertz. So if you look to the antenna theory, you see that, especially for antennas, everything is scalable. The same applies too for semiconductors, by the way. In semiconductors, the difference between a transistor working in kilohertz range, megahertz range, gigahertz range, what is the difference? Actually, if you look to the structure topology of transistor, it is more or less the same. If you have a field effect transistor, what is the difference between FET working at a couple of hundred of megahertz and FET working at millimeter wave? The structure is the same. The only thing which you ask for is the flight time of an electron or of a hole from source to drain should be much less than a period of the signal you are dealing with. Because otherwise, the electron or the hole will experience multiple periods, so it will average out and it doesn't see anything. Okay? So therefore, for the perfect or correct operation of a semiconductor element, the transit time of any of its carriers, charge carriers, whether it is holes or electrons, the flight time must be much less than a period. So that when it goes from source to drain, it sees as if it sees a constant field, so that it can react to the signal. Okay, this means, and the flight time, as you see here, irrespective now maybe of epsilon r of the gate or something like that, it is something like it goes like C naught. So therefore, flight time is directly related to the physical length. So you can scale down, and you have a transistor principally, and you have a transistor working in millimeter wave. Therefore, if you are involved in semiconductor manufacturing, you hear 30 nano technology or 50 whatever. So this is actually how big are the dimensions you can invent. But more or less, transistor is transistor. Even if you go to the terahertz range, you have the same transistor, and you have the same equivalent circuit and everything which you used to use. Okay. So as you see, you scale linearly for semiconductors. You scale linearly for antennas. Maybe with some exceptions, it is more or less higher frequency, smaller systems. Okay? And if we relate this to fractional bandwidth, as a rule of thumb, fractional bandwidth, wideband is, say, 20% fractional bandwidth, not a bandwidth, fractional bandwidth. Narrowband is 1% fractional bandwidth, but it remains narrowband or small or wideband by 10 giga central frequency, by 100 giga central frequency, or by 1 tera. So now we can understand terahertz must offer us higher resolution. Millimeter wave is lower resolution, but it's still better than microwave. Microwave is still better than if I work now in the megahertz range. Resolution is clear. Bandwidth is related to resolution based on this very, very simple primitive model, and based on the rule of thumb of fractional bandwidth. So the higher the frequency, the better the resolution. But this is not all. You may have noticed that in my model here, I implicitly assumed that when I illuminate from one side, the wave goes through the first layer, unattenuated, partially reflected at the first interface, goes unattenuated, partially reflected, unattenuated. So the framework of the whole thing here assumes that the wave can propagate through the entire structure unattenuated. Now we ask ourselves, is this correct or not? So the theory applies as long as the wave can penetrate. This is called penetration. The wave here can penetrate and goes and collect information about the body and comes back as a scattered wave. Collect and comes back, collect and comes back. This is a process of imaging. So you illuminate and let the wave goes through as long as the wave is strong enough to propagate into, interact, and come back with information about the structure, you are fine. So therefore, let us now move. We discussed the issue of resolution. Let us now go to the issue of penetration, of transparency of the material. We call it, the material in this case is called transparent, which means the wave can propagate unattenuated through the entire structure and collect information and come back with it. This is a transparent material, or the wave can penetrate. Theory, or the electromagnetic theory and the theory of physics tell us that there is no material in this universe which is transparent for all frequencies or which is dark for all frequencies. Let us now maybe to define what I mean with dark. Dark means you go, the wave interacts with the material consumes the power, the energy of the wave, and the wave becomes weak, and upon becoming weak, it cannot propagate anymore. So this is until certain depth, it can propagate, it can penetrate, and afterwards it is too weak to further propagate and to collect information about the rest of the body. Okay? In this case, we call the object to be imaged dark. Dark, really dark, if the wave cannot penetrate at all. So it goes like metal. Metal you cannot penetrate. It is really dark. We have something in between. If you can penetrate, say, a couple of millimeters, couple of centimeters, and afterwards the wave attenuates. So in this case, you can have information about the first few centimeter, millimeter. As you see here from my talk, I never talk about certain numbers because numbers are related to frequencies. So I say sometimes millimeter, micrometer, and so on. If you would like to know how much, you must tell me, okay, which frequency are you going to use? Let us now go to some physical aspects. What is the reason for being dark or being transparent? Physics tell us that any material is in continuous interaction with its background. Any material is composed of molecules. If you have solid state, the molecules build a crystal. They build a geometrical structure. And these molecules, because they have charged particles, they are surrounded by the background radiation which comes from the sun. As long as you have temperature, you have a background radiation. Okay? You have now charged particles. The charged particles are accelerated by the electromagnetic wave in its vicinity. When they are accelerated, they start to radiate. So they absorb to be accelerated, and when they are accelerated, they re-radiate. And if you achieve the state that on average the amount of absorbed energy is equal on average to the amount of re-radiated energy or power, in this case you are in a thermodynamic equilibrium. Thermodynamic equilibrium means that you absorb as much as you emit on average, which means I don't follow an individual molecule or individual parts, I mean on average. And this is a definition of thermodynamic equilibrium. Now, some materials, because of nonlinearity, some materials, they absorb at a frequency and re-radiate at another frequency. And this is actually the main problem here. if you say absorb at blue, optical blue, and re-radiate at infrared, so actually you consume the power or the part of the power of the optical spectrum in the blue, absorb the blue, but of course the energy must be re-radiated. It is re-radiated, say, in the infrared. So you absorb blue and you become hot. Okay? This is one of the mechanisms why for a certain material it is in a balance, because it absorbs exactly like it emits. If you are lucky, you absorb at a certain spectrum and you re-radiate at the same spectrum, so you don't feel anything. You absorb and re-radiate at the same frequency. But if you have a darkness in the material, this means at this frequency band, the molecules, they interact with the incident wave and absorb energy from the incident wave and transfer this energy in something else, say thermal loss. So now you don't see your original frequency anymore. Okay? And this will happen actually at resonances of the molecules. So the molecule interact maximum when the frequency of the illuminating wave are near to their resonances. Imagine that these molecules, they dance or they oscillate in x direction, y direction, z direction, and high temperature means they oscillate. Temperature has nothing to do with the frequency, but it has to do with the amplitude of oscillation. And maybe they rotate in this direction, in this direction. So they have a total of 6 degrees of freedom, translational, x, y, z, and they may oscillate this way, and this way, another 6. Okay, and sometimes for some particles, you may also have what is called spin. This is what we treated in our magnetic resonance. So each of these oscillations has a certain spectrum. If the applied wave has the proper polarization, which means, okay, I am assisting this, or I am assisting this, or I am assisting this, or I am assisting this. So any rotational motion will be assisted by circularly polarized wave. Any translational motion will be assisted by linearly polarized wave. Depending on you are coming from here, you are coming from there, especially in crystals. Why do you see crystals are lightning in a certain direction, in another direction? Because actually it depends now on, you come with certain propagation direction, you come with certain polarization, and now you can excite this one, and you see it very, very, very bright. Okay? So more or less, if you now consider the entire frequency axis, you will never find a material, whether it is in gaseous status, in liquid status, in solid state, which is dark forever for all frequencies, or which is transparent for all frequency. Because you are near a resonance, absorbs, and you are the material is dark. Now you leave this frequency band and you go to another frequency band where the interaction itself is weak, so you are transparent as a material. So, and this is governed actually by a very, very nice relation. It's called in the literature KK relation. The KK relation, the K and K, I always forget the names, but these are two scientists who proved, and maybe you had these ones, that the real part of the permittivity and the imaginary part of the permittivity, they are related by what is called Hilbert transform. The real part is a Hilbert transform of the imaginary part. The imaginary part is a Hilbert transform of the real part. Therefore, you cannot have something which is zero forever. I mean, now if you consider losses, you ask for 0 epsilon double dash. You will never have this, because this will also indicate the Hilbert transform of 0 all over the frequency is 0. So you have actually a complex permittivity of 0. There is nothing like that. Okay, so why I tell you that? Just to see that we have, in addition to the bandwidth, which dictates the resolution, we have also the penetration. as a rule of thumb, for known materials or for materials which are relevant to us, the lower the frequency, the higher the penetration, as a rule of thumb. Except, as I told you before, except for if you are near to a resonance of water, and you have foggy weather, for example. Now you have a propagation near the resonance of the H2O, so you have a very, very high attenuation because you have water in the air, and this water so absorb because of the vicinity of the frequency, and the wave itself cannot propagate anymore. I think that Dr. Akhtar yesterday talked about this attenuation diagram as a function of frequency, just to let you know. Did he? Because we had a short discussion the day before yesterday, and we thought that maybe it is good for you to understand why usually you use certain numbers for the frequency. If you have already noticed that, you see, or you may hear, we have the BMW cars. They are equipped with radars at 24 gigahertz, and you always hear 24 gigahertz. The VW, Volkswagen, they have at 77 gigahertz. And I don't know now exactly the three frequencies, 24, 77, and 94 gigahertz, which belongs to what. But I know that we have three big car companies in Germany, Volkswagen, BMW, and Mercedes. And I know that each company uses one of these three frequencies. And now you ask yourself, why 24? Why 77? Why 94? And now you may also have heard about the standard in the wireless communication of AD. You know, IEEE 802.11 AD. Have you heard something about that? In AD, you are working around 60 gigahertz. And you hear from time to time, we would like to build a 60 gigahertz system. In the submillimeter wave imaging, you talk about the 140 gigahertz or 220 gigahertz. These specific numbers, they are actually related to the atmospheric attenuation at these specific frequencies. Okay? You can measure the atmospheric attenuation as a function of frequency. So you will find out something like that. Maybe it is now not directly related to. So if this is here the frequency, and this is here A of F, so A is attenuation, maybe in dB. So actually you have something like that. So the attenuation goes higher on average as the frequency goes higher, or it goes down if your abscissa is the wavelength. So usually physicists, they prefer wavelength to talk about. We engineer, we prefer the frequency. Okay, and if you look to these frequencies here, they describe these well-known frequencies. This is for atmosphere. You may tell me, or you might ask you, okay, minimum I can understand why I am using minimum. But you will be surprised to know that the 60 gigahertz is at maximum, not at minimum. Do you know why? Although anyone can say, okay, I can understand you would like to work at a minimum because I have a minimum. Of course, it is a local minimum. It is not an absolute minimum. But in fact, there is, in these aspects, especially for communication, in these aspects, there is no big difference between working around minimum and around maximum. You would like to work around a place in the curve where the tangent is horizontal, because in this case, your system is wideband. Whether it is minimum or maximum, especially for communication, you would like to have minimum distortion. And minimum distortion, if you work around minimum or maximum, you don't have a big change which causes amplitude and phase distortion. So therefore, especially for communication, you work around either minimum or maximum. Of course, for penetration, for imaging purposes, you would like to work around a minimum, but this is not a must. Okay, important is to have a flat, whether it is minimum or maximum. And this also explains to you why there are specific frequencies around which we are willing to work. Now, back to the penetration. Beside this attribute, we should also, for a specific imaging, we should also, beside the resolution, see how deep can I penetrate. In terahertz imaging, you are happy to penetrate a couple of millimeters. This is a penetration, independent of the resolution, because the resolution is offered. If you have 600 giga and you have bandwidth of 10%, even if you have a bandwidth of 1%, from 600 you have a huge bandwidth of 6 giga. So the resolution is not an issue around this very, very huge frequency. The main problem is how deep can you penetrate, how deep can you get the information and come back. Clear? So we discussed now resolution, penetration. And it's clear for you. And we are still in one-dimensional. We just would like to get the information, the depth information. The other two dimensions, the transverse or the surface imaging, has nothing to do with all this discussion. It is an antenna problem. I will show you that if we can have high directivity antenna, we solve the other problems. But the same discussion applies. Let us concentrate first on the one dimension, how I go along the depth dimension. Okay, another problem regarding instrumentation. The higher the frequency, the more difficult is to have a system producing enough power. Just see how much power can you produce at 50 hertz. So the entire electricity supply, nearly with no limit, because you can use it also mechanically, 50 hertz. But now ask yourself, okay, how much power can I use in X band? Those of you who spend their military service in a radar station, you can have pulsed power of megawatts, but just pulsed, just for radar. If you go to the millimeter wave, so instead of talking about megawatt or kilowatt, you are very, very modest. And if you go to sub-millimeter wave, you are happy if you have just a couple of microwatt. So in other words, the efficiency of generating waves, generating enough power, as a rule of thumb, goes down as the frequency goes higher. So now we see penetration goes down, resolution goes up, but we have also the other problem is can I produce enough power or not? Of course, one of the techniques used for producing high power is to have multiple sources and to conduct what is called power combining. The power combining, I know that I deal now with different aspects, but believe me, they are related to each other. Because if you are building an imager, so you need to generate the power. And now the question, can I generate or not? Imagine that each individual oscillator can produce 1 nanowatt. I'm just giving an example. And you would like to power combine, say, 1,000 of that in order to have 1 microwatt. Principally, you say, okay, nothing. So I will have the oscillators and combine the power. If I have 1 nano and I have 1,000, I will have 1 micro. But the problem is the phasing. The phasing, and for those of you who work at lower frequency, power engineers, you know that if you have multiple stations, multiple machines, multiple generators, and you would like to combine them in a network, the most difficult problem is how to bring them in phase. Because imagine in the worst case, you have 2 oscillators, one achieves maximum and the other one achieves minimum, they cancel each other. So the problem is in power combining in order to produce more power is how can you align the phase of 1,000 small oscillators so that they are added constructively. They don't cancel each other. Therefore, I told you maybe yesterday or the day before that sometimes you use antenna technology for power combining. Because if you build an antenna array with a pencil beam, you know that this antenna array will concentrate the radiation in a certain direction. So let us connect the oscillators to the different elements, and they will combine together along the main beam. Okay, and if I have my receiver at the main beam, I collected the power already. On the other hand, if you insist to work with wired network, you will have lots of problems. Just the tiny distance, the length difference of this line or of this line, especially at higher frequency, will cause a phase mismatch, and you lose the synchronization. So this is also one of the problems you must consider in the practical imaging. So you may say, okay, I would like to work with such resolution. Millimeter wave will not offer me. So let me go to the terahertz. Terahertz imaging can offer this resolution. Now, can I penetrate? Okay, I can penetrate to the depth which I have to. And then the next problem, can I have enough power or not? Especially in terahertz, because I think the title of the whole series has also terahertz. Especially in terahertz, just as an overview, how can you produce a terahertz signal? Terahertz is something between optical signals and millimeter wave signals. In millimeter wave, we can say, okay, we are done. So we have semiconductors producing this. So if you can have a transistor, you can have an amplifier. And from the amplifier and feedback, you can have an oscillator, and you are done. Right? For any frequency band, just have the amplifier. If you have the amplifier, and what is the essential part of the amplifier? A transistor. Have the transistor. In the past, we had also the pentode or the diodes, but now we are. So the most important element in a frequency band is a transistor. If you have it, you can have the amplifier. If you have feedback together with the amplifier, you can have the oscillator. You can afterwards use subharmonic PLL, phase locked loop, and so in order to have clean spectrum. But the essential element in a frequency band which allows you to produce signal, to make the signal processing, and to do everything which you wish, whether it is communication or imaging or whatever, is that transistor. As I told you before, we have problem with the transistors. If this is the transit time. The transit time goes down as you raise the frequency. So you will need to bring, say, for field effect transistor, the source nearer and nearer and nearer to the drain. Okay? Or in a bipolar transistor, the base itself will be narrower and narrower and narrower between emitter and collector, right? You can say, okay, what's wrong? The problem is you usually work with biased situation. So you apply a DC voltage. And in order, for example, to have a bipolar transistor conducting, you must overcome something like 0.3 volts, 0.6, depending on the material you use. So now you bias with DC, but it's very, very near to each other, and you have the problem of breakdown. Because now you brought things nearer to each other, and due to the biasing, you get breakdown immediately. How to solve this problem? So this means at certain limit, we will not be able anymore to have transistors. And if we don't have transistors, we cannot have amplifiers, we cannot have oscillators, forget the whole frequency band. So one of the techniques to overcome this is to invent new materials with higher breakdown, or maybe this is also the relation to nanotechnology. I can have a long physical length, because I told you the flight time of the charge or of the charge carrier should be much less than the period of the wave or of the signal, right? So the flight time is not the distance. Flight time is distance and speed. And do you remember the semiconductor? The speed of a carrier is related to what is called mobility, right? The mobility, therefore, was NBN was better than PNB because the mobility of electrons were bigger than the mobility of holes and so on. One of the, and if you still remember the mobility, I go now, if you have the omega k or energy k diagram of a lattice, this is something related to physics, you had the band structure. The band structure, you have something like that, like that. Let me make it a little bit. Do you remember these figures? This is the band structure. Let me make it a little bit. The effective mass of the hole of the electron is inversely proportional to the second derivative to the opening of these things here. So in order to, say, enlarge the physical distance and nevertheless to have a speedy transit time or faster transit time, we can have carriers with higher mobility. And one of the techniques for doing that is to invent a new material by adjusting the doping and so on. This is actually semiconductor research, in inventing a new material for which these energy gaps are as narrow as possible, because 1/over is lower effective mass, and lower effective mass means higher mobility. So in this case, my electron, my hole, is very, very fast, so that I can have a short transit time, and at the same time keep the distance between the source and the drain big enough to avoid breakdown. Okay? So this is actually, maybe if you remember the gun element. The gun element you had, but not for this purpose. In the gun element, you had also two areas like that. And most of the carriers were collected in the first cluster here, and at a certain applied voltage, they go to the other one. All of a sudden, so they become faster, and this is actually essential for the operation of gun element. Okay, if you still remember what you had in semiconductor physics. But this is again another mean of having faster carriers. So I can use, and this is actually why do you hear we have gallium arsenide technology, we have CMOS technology, we have indium phosphide technology. The difference between all these technologies is how fast can I have the carrier? But the transistor is the same. The structure itself is the same. No difference. The only difference is how can I overcome the problem of transit time. Okay, but all these have been exhausted up to, say, 30, 40 gigahertz. What can we do to generate? Not to amplify, to generate. You have another technique which is called frequency multiplier. So you can make use of a very simple nonlinear diode. And if you have nonlinearity, you have harmonic generation, and you can input, say, 10 giga, and maximize the operating point, or adjust the operating point to, say, maximize the third harmonic or the fourth harmonic. One of the problems related to that is the efficiency. Because you may, if you have efficiency 1%, so you inject at 10 giga, say 1 milliwatt, and you get 0.01 milliwatt as a third harmonic. So this is one of the challenges. Just to see the problems, the possible solutions, and how can we overcome it, and with which price can we overcome. So the frequency multiplier is a technology of raising the frequency. The main oscillator itself works at 10. It needs the amplifier, the phased-locked loop, and the feedback, and all this stuff. And all what I'm going to do is just to take the power and generate the third harmonic. So you are able, till now, for generating sub-millimeter wave or terahertz signals. So in many literature, you can read 10 times. So that if you can generate 30, so time 10, 300, and you are within the terahertz. Okay. So frequency multiplier is one solution. But there's a second solution for producing terahertz signal. The second solution is coming from the optical. Laser generation is not a problem nowadays. You can buy the laser pointer for maybe 10 cents. So to generate laser nowadays, the technology is mature, and you can generate laser different frequencies, and you can have everything. Good phase locking and all this stuff. Now the other way of producing terahertz signal is to mix two lasers with frequency difference which lies in the terahertz range. You are dealing now with multiple tenths or multiple hundreds of terahertz. Now if you have two lasers with nearby frequencies, so that if you mix together, as you know, any nonlinear effect will mix, so you will produce the sum of the frequencies and the difference. So adjust or take your input and adjust the difference to lie in the terahertz range. But again, you have a miserable efficiency. I still remember as people maybe 10 years ago started to talk about terahertz imaging and how to generate and so on. So you attend a conference talk, and they talk very, very proud. So we got 0.1% efficiency. Whether you frequency multiplier from down or mixing two laser signals. So this is the order of magnitude of production. But sometimes you say, okay, this is the only way, I have to accept. But just for you to understand what are the challenges. So again, we would like to raise the resolution. We go higher with the frequency. But what are the challenges facing us is actually the penetration. You have less penetration, and you have difficulty in producing enough power. And both are related, by the way, because you may say, okay, if I have 1 dB per 10 meter, attenuation. I may raise the input so that I have enough at the output. So if you raise the input, but the input itself is really very, very measurable. So you have double trouble. You have low level of power and high attenuation. The research in graphene. Is any one of you involved in graphene or nanotechnology? So, graphene, because it is also one of the means by which you can solve the problem of terahertz generation. Graphene, if you look to the atoms of carbon, they may connect together in generally two fashions. One is graphite. The graphite itself, the atoms, they build hexagonal structure, and they are tightly related to each other in a planar structure. But from a plane to plane, they are loose. And this also explains why you use graphite for lubrication. So it can slide over each other. The other structure is diamond, where the atoms are near, very, very near to each other, and they build a very, very solid bond. So the distance also in all three dimensions between the different atoms is the same. This is the diamond structure. The graphite structure, as I told you before, it is layers of thickness 1 atom. And these layers are loosely tied, or loosely related to each other, so that you can slide a layer over the one, or the layers over the other. If you now succeed to have is just a single layer graphite or graphite, so the German pronunciation is graphite, single layer graphite, so which is just single layer, and these atoms in hexagonal, so take the hands of each other, building this hexagonal structure, but there is nothing down and nothing above. Okay, this is a single layer graphite. It's called graphene. And now physicists, they studied the band structure, which we. So I'm not good in drawing, but the band structure itself, it's something like that. Say this is kx, ky in only in one, because you have only 2 dimensions. So you have the k vector is only 2 dimension, and this is the energy W or E. So they build something like the umbrella. So if you go to big airports and so on, sometimes you have this umbrella with the spikes here. So if you know what I mean, or not? Have you seen in the front of airport or something like that, you would like to have big umbrellas? So actually you extend a big sheet between some bellows. And so if you look at it from above, you will find how they looks like an umbrella, but it's fixed at 4 points. Or so can you imagine now that this is actually the band structure of graphene? And can you tell me what will you say immediately if you see this spike here? What was actually the effective mass in the last one? We said that the effective mass of the carrier, the charge carrier, is inversely proportional to what? To the second derivative, to how sharp this is. Here high effective mass, here low effective mass. If you see this now, if you have a carrier here or there, what is the effective mass? The curvature is infinity, okay, because the curvature, and the effective mass is ideally 0. And this is actually this is the hope of solving terahertz, because if I use graphene in my transistor, till now the technology is not so mature. But as you see here, we have now structures in which you can achieve not necessarily infinite is the theoretical limit, but you can achieve very, very low effective mass. So actually nearly zero. And what does this mean? I have high mobility electrons or high mobility holes, because if the carrier is here, it's called hole. This is the band gap. If the carrier here is called electron, but in both cases it's electron. So the carrier here or there, here it's called hole and here it's called electron. And its effective mass is inversely proportional to the curvature, which means the sharper this peaks here, the lower the effective mass. And the ideal structure of graphene, if you really succeed to have a big area of single layer graphite, single layer structure. I don't know whether you heard how first experiments were done for producing graphene. It's very, very, very interesting story, because these were two scientists in an American lab, and they started by having graphite in pulver, in powder, and put it in Scotch tape. And with the Scotch tape, they pressed it, and then open the Scotch tape. Now you have half and half, and you take this and you press it again. So because graphite itself is like lubricant, the layers are sliding over each other. If you repeat this many, many times, you can achieve, of course, not a complete plane. It has some holes, but you may have some small places where you have only single layer current. Whether it is holes or a double layer or three layers, it is the same problem. You need just single layer in order to have this. You deteriorate the performance, and this is what's called now nanostructure or nanotechnology. The nanotechnology, one of the applications in nanotechnology is to produce graphene. If you now integrate graphene in a FET, field effect transistor, you can Google and look. You have plenty of publications. You can overcome the problem of, I would like to have high mobility. So I can now have a finite distance between the electrodes, between say source and drain in a field effect transistor, and nevertheless I have high mobility charges or charge carriers, so that the transit time is really very, very low. And I can have now bi-transistor. But again, the main problem is the efficiency. So the technology is not yet so matured to have acceptable efficiency. But more or less, you need to have first the first generator. You may use the power combining. If we now talk about the power combining, do you think what could be the main challenge in power combining at terahertz? Is the phasing. Because now you are working, you would like to adjust the maximum of cosine, and this cosine, the period itself is extremely short, and now you would like actually to adjust from, say, 10 or 20 or 100 oscillators to adjust the peaks of these cosines in order to add together constructively. So the challenge here, so you may have measurable oscillators, and you may say, okay, I can power combine everything, but the main challenge is, again, how to align, how to phase align all these in order to add together. Okay? I believe that I gave now a wide overview about two issues or three issues. The first issue was the resolution. The second issue was the penetration. What are the physical background for penetration? Generation of the signal is tightly related to what is called terahertz imaging. How can we generate terahertz signals? How can we power combine if it is possible? Of course, power combining 100 is much more challenging than power combining 10. Power combining 10 is much more challenging than power combining 5. But you know now, at least, if you read some article about that, you know now, okay, why I power combine, why I am looking for inserting graphene, say, in a transistor in terahertz generation, why I'm mixing two lasers, or why should I have higher efficiency in the 10th harmonic generator or 20th harmonic generator. Okay, you have now three categories of generation: either frequency multiplier, low efficiency, or mixing two laser signals, or succeeding in having the classical way of generation, which starts with amplifier, oscillator, and then afterwards, maybe to have the freeze looking in order to have high spectral purity. Okay. So, Dr. Zubair, where are you? So, till when should I continue? So, it's up to me. What is your pain level? So, okay, good. So, maybe we can now go from the discrete to the continuous, so that we see the nice relation between the profile as a continuous, not in a step function, but a really continuous distribution. Okay, and maybe in this context we can also see the resolution from another perspective. Okay, do you have a question before I move to? So everything which I told was understandable? Yes.
Actually, in X-ray image of any body, the resolution is very high.
Yes.
It means the X-ray to penetrate all through the body.
Yes.
So how it happens? I mean, since X-ray should have much less penetration level.
No. This is a good question. He compares now the relatively low frequencies, where we are still working with continuous field distribution. Yeah, we should go now to the relativity, or to the quantum mechanics. He claims now X-ray is high frequency. And high frequency, I said, the penetration goes down. Goes down as long as the frequency is still, say, optical range, or say. But if you go now to the X-ray, the ray itself doesn't. It goes through the spaces between the atoms. The photon itself is so small, then it is not considered as a continuum. Where you say, okay, I have electric field distribution, magnetic field distribution, and I can define permittivity and permeability. Look, in our model here, we assume that we could smear out the microscopic properties in a macroscopic property. So, as you see here, I consider everything is continuous. I didn't go into the level of atoms. I didn't go into, as I told you, absorption. Again, when I calculate absorption, when I calculate epsilon r and epsilon r dash and epsilon r double dash, I calculate the macroscopic. And macroscopic is I smear out. I consider the phenomena itself, the material is not capsular, is not molecules and so on. It is continuous distribution. The wave is continuous distribution. The quantum mechanics tells us, this is nice, until the wavelength becomes in the same order of magnitude like the atoms and the molecules. In this case, you cannot do it this way anymore. In other words, the quantum mechanics tells us this, say, imagine that you have a sheet of sheet of line, so any sheet of paper, okay, something like that. This is a continuum, okay. If you have a glass and you enlarge, you will find out that it is a net, not continuous. Exactly the same happens to the electromagnetic wave distribution. If you go with a frequency very, very high, you don't have this continuous distribution that I say electric field all over the place. Okay? In this case, you will have packages of energy, which are called photons. And now, forget now the electromagnetic theory we know, or this field theory and so on. You deal with these things as if they were particles. Now, you have a photon, and you have an electron or atom, and it collides. So now you return back to the mechanics. And this applies to beta radiation, gamma radiation, and alpha radiation. X-ray is some sort of gamma radiation. So the frequency is so high that you don't deal, and this explains also the penetration, you don't deal with the classical electromagnetics. Now you have photons, and these photons are going through the material, they penetrate, okay, and they scattered, not our scattering now with reflection coefficient and so on, they scatter because they behave like tiny spheres which are collided with this, and they go here and there. So you have a completely different approach, and everything which I told you about the electric constant. The electric constant is essentially a macroscopic, not microscopic, a macroscopic quantity, which means I assume that my material is smeared out. I have a continuous. So you cannot define for interaction between photon and electron, you cannot define a dielectric constant. What is the dielectric constant? The dielectric constant, return back to the definition, it was so. I assume this is my atom for the simplest model. This is my atom. I smeared out the electrons around the atoms in a cloud. So here. This is minus. Now I apply electric field. So the positive charge will go this way. Then the center of the negative charge will go this way. Right? Now I have a dipole. And this dipole will oppose the original electric field. And this opposing, this effect is averaged out and saying now I have D, the flux density is epsilon naught E plus B. So this is the definition or the way you define. You assume that this microscopic were averaged out, giving rise to this epsilon of XYZ. If you go now to gamma rays or to Rontgen, we are dealing with a completely different thing. We don't have permittivity anymore. We don't have permeability anymore. We have now particles, even if it is radiation, they are called photons, which are interacting with each other. So therefore, Rontgen is a completely different theory, completely different treatment. Have I replied your question? Okay. Of course, this is also maybe the good time to talk about ionizing. Because one of the problems with Rontgen or CT, because CT is Rontgen, CT is X-ray, but you make it in a certain way. So you have the source itself, and the source say you make a tomography, because therefore it is called computer tomography. So if you would like to have an image of this plane here, you have just one source or multiple sources, and you emit from here. It's also transmission type and not reflection type, and you receive from here. And then you rotate the whole thing, okay? And you can show very, very clearly using very simple equations that if I measure for each, so I emit from here and I measure from the opposite side. If I have this attenuation as a function of phi, of angle, Okay, I can process the data and I can tell you the absorption of the X-ray at each individual point. Okay, but again, this is a completely different type of imaging. It's called also transmission type imaging, in which you need access in front of the body and behind the body. The reflection imaging has the advantage that you can stay on only one side of the object, and nevertheless you can have the image. Okay. Okay, so now let us see what would happen when we make our delta t, because it's our choice, smaller and smaller and smaller and smaller. I would like to come to the situation where I have a continuous profile. Let us first consider what was Rn. Rn was defined as a local reflection coefficient between epsilon Zn plus 1 and Zn. So you have Zn plus 1 minus Zn divided by Zn plus 1 plus Zn. Right? So you have actually from here, this is Rn. So you have here Zn plus 1, and here you have Zn. And you measure the reflection here. Imagine now that this Z is a continuous distribution, so that you can say this one here, let me make it this way. This is actually Z, this is X, this is Z of X plus dx, or let me make it as a T, because we are still working. So this is here of T plus dt, and this one here is Z of T. Okay? So I have a continuous distribution. In this case, Rn itself will be, I would say it R of T, which is, because it is at a certain place, which is, if you have Z of T plus delta T minus Z of T, it is actually Z dot of T times dt. I prefer to use dot for the time derivative and dash for the x derivative. Therefore, I used here dot. You may still remember the first semester of your engineering studies, or you use dot. So this is the derivative with respect to t. Okay, this is the nominator. The denominator is z plus z. So you can say they are very near to each other. I can say it is twice z of t. So this is Rn. Okay? And we know that Rn local will produce outside the body the same Rn, but phase delayed by twice omega t, Tn. But Tn is our t now. So we will have here at the end only as d r bar, because r bar is the frequency which we measure outside the body. So it is here r of t e to the minus j twice omega t. T, the position where I'm staying. Okay? So in this case, as you see here, it is 1/2 of z dot over z e to the minus j twice omega t dt. This is dr. right? I think going from one to the other, this transfer is easy. Okay, and now I add together all these contributions. So I will have integral. So I started actually from 0 and maybe to a certain maximum, say, call it capital T, I don't know where, of 1/2 z dot over z e to the minus j twice omega t dt. This is actually R, the entire R as a frequency of omega. Is it right? So this is actually go from the discrete to the continuous case. Now z of t is the local, which is related, of course, to epsilon, to the dielectric constant. This is the local impedance. It varies from position to position, but I still have it as t, as a function of the flight time and not function of the position. We will have the transformation later, or the relation between t and x in the continuous case later. Okay, you should here consider the fact that this is a derivative. In any place where you don't have any change, like the place in front of the object. In front of the object, this was actually the negative x domain. You have epsilon naught. So you have the same z, so that z dot is 0. Right? And if you have certain profile, it will end at certain point. And after that, up to infinity, z dot is also 0. So z dot describes only the place where you have change. And this will relax my integration here. I can now very, very quietly write down this as minus infinity, and this is plus infinity, because I know that the reflection will be caused only by the change, by the profile. But as long as I don't have a change, I don't have a profile, it is 0, so I can relax the definition into R of omega is integral from minus infinity to infinity 1/2 of z dot over z e to the minus j twice omega t dt. Okay? What is this? This is, except for this stupid factor 2, it is a Fourier transform. So it tells us that the reflection coefficient measured in the negative x region, as long as I am sure that from minus infinity up to 0, I don't have any profile. The reflection coefficient measured as a function of frequency is not more and not less within the framework of our approximation, within the framework of our Born approximation, zeroth order, or low contrast approximation, or small reflection approximation. These are different descriptions for the same thing. The measured reflection coefficient is, as a function of the frequency, is, except for the factor 2, I think we may make some variable transformations in which we interpret delta t not as just one, not forth and back, but the same, the entire flight time. In this case, we will have, because I don't want now to make additional complication by variable transformation and so on, allow me to rewrite this with omega, only with omega, without the factor 2. Of course, you can work. You can say, okay, my delta t, original delta t, was not the simple way, but it is forth and back. In this case, you don't have the factor 2. So in general, we can now write down R bar of omega is integral from minus infinity to infinity of, let me call this g of t. So it is g of t e to the minus j omega t dt, where g of t is 1/2 of z dot over z. The profile reconstruction becomes now very, very simple, because you can say g of t is 1/2 pi integral from -infinity to infinity of r bar of omega e to the plus j omega t d omega. And this is our reconstruction equation. Excuse me?
Can you scroll up?
Yeah.
That is J2 omega t, correct?
No, I told you now. I told you, I know that
Okay,
yes, I will take t as back and forth because I don't want now to unnecessarily make a variable. I needed to have the 2 in order to explain it to you. But of course, you may redefine t in such a way it is not the distance, but double the distance, the time distance. Okay, in this case, you don't have an issue with the factor 2 anymore. Okay, but I intentionally started by the simple time distance, but you can redefine it as twice this time distance, so that you have the classical or the traditional form of a Fourier transform. Let us okay, I think I can continue a little bit by considering the resolution again, but in terms of the Fourier transform. Now, the problem is if you reconstruct it, so you conduct the frequency measurements, the reflection coefficient as a function of frequency. Of course, we have here the big problem that we should measure from -infinity to infinity, or as a frequency from 0 to infinity. We will consider this later now as in the context of resolution. But let us first see, upon having g of t, how can I get z dot? How can I get z? Because I'm looking for z of t. So z of t is the looked for quantity, and from the inversion, from the profile inversion, I get g of t. Now write down g of t is 1/2 dz by dt divided by z of t. I think it is given this way, right? So this means you have dz over z is twice g dt, right? So this means ln, or len of z, if you integrate, say, from 0 to certain value t, is integral from 0 to t to g of t dash dt dash. I think this mathematics is clear for you, or you need explanation. So it is a simple solution of a differential equation. So this means we may write down z of t is z of 0 e to the plus twice integral from 0 to t g of t dash dt dash. And this is actually the expression we may use for retrieving the, so we measure first the reflection coefficient as a function of frequency. We perform an inverse Fourier transform. Upon having g of t, I can retrieve z of t. This is actually my quantity which I'm looking for, and I get it from, in terms of g of t, this way. It's actually very, very direct method. Okay? Any question because before going now to the issue of resolution, I will finish 4. Is it okay with you? Okay, so after 4, I think all of us are not strong enough to continue, including myself also. Okay. Let us now consider the practicability of the Fourier transform, or of the inverse Fourier transform. This expression here tells us, okay, I can get g of t if I perform inverse Fourier transform, which means I can get g of t if I would be able to measure the reflection coefficient for frequencies from 0 to infinity, or from minus infinity to infinity, because it is only artificial, this from minus infinity, because you measure at a certain frequency. And the question now, is it feasible? The answer is no, because I can't measure from minus infinity to infinity. Now let us assume that, okay, I agree, I have measurements only within a certain band, and let us start with the base band. I am able to measure from 0 to a certain maximum frequency, say capital omega. And let us see what would happen if I use these limited frequency data for my construction. In other words, let me assume that I'm not able to retrieve G. I will retrieve something else. Let us call it estimation G hat. G hat of t. I define it as a limited bandwidth Fourier transform as 1 over twice pi integral from minus, say, frequency capital omega to plus capital omega of r bar of omega e to the j omega t d omega. So I will define it this way, because I'm not able to measure from minus infinity to infinity. Agree? Okay, now the logical question is, what is the relation between g hat, which I constructed here based on band limited information or reflection coefficients, and the original image g of t? So you may make some simple substitution. You say g hat of t is 1 over twice pi integral from minus omega to plus omega e to the minus j omega t d omega, and I will write down r in terms of its original expression. It was integral from minus infinity to infinity g of, because I am not allowed to use t again, I will call it t dash, e to the minus j omega t dash d t dash. So I just wrote r bar of omega in terms of the original g of t, because my goal is, what is the relation between g hat, which I can really reconstruct based on the limited bandwidth measurements, and the original image which I'm looking for. Now you may exchange the two integrals, because you have now two integrals. You can say, okay, I'm actually integrating from minus infinity to infinity t dash, g of t dash, and I have here this form, 1 over twice pi integral from minus omega to plus omega of once e to the minus j omega t, this was plus, sorry. One's plus, one's minus, so we have actually e to the minus j omega in t dash minus t, d omega. This is a very, very, very simple substitution. Correct? So it gives us the relation between what I can have based measurements, and what I'm looking for. I am looking for g of t, and what I can reconstruct is g hat of t. So let us call this one here d of t dash minus t. I think you will recognize immediately it is a sinc function, right? So because so d of t itself so forget the peak now, because the peak should be proportional to the bandwidth. And we have the first zero here is when capital omega times t is equal pi. So we will have here, this is pi over capital omega. Here it is twice pi over capital omega. Here we have 0 minus pi over capital omega, and so on. So this is actually the d of t dash minus t. So, and you can recognize now that we are convolving, because what is the form which you know, which looks like f of x dash g of x minus x dash, or x dash minus x dx dash. This is a convolution. So this is as a conclusion what we get from limited frequency measurements is the convolution between this function here, this sinc function, and the original image. So let me remind you what was the convolution. So actually you can say this is t dash, and this is, say, your image g of t dash. You bring d of t minus t dash, put it here, this is t, and this is here g of t minus t dash. It is centered around t, because the maximum is when you have the argument is 0. And how can you construct g hat? So you take this as a flag and run along the t dash axis. The flag is situated at t. Each time you take this function, multiplied by the, I will call it infinite resolution image, because this is actually the image which we would have if we measure over the infinite bandwidth. You take this here and run. At each point, you multiply by the function, and because this is compact, so you will actually mask only this part of the function. Integrate, and this is your g hat. So g hat itself is something like weighted average. What is average? Average in general, or what is called sliding average. In a sliding average, you go along the curve and take a certain range, and you average out. And sliding, because you run. You know the expression sliding average? It is not averaging over a fixed period, but you have a flag. In the sliding average flag, your flag is a rectangular pulse. And you run with your flag along the t dash axis, and at each point you average out. This sliding average. We have also here a sliding average. Convolution is a sliding average, but it is weighted average. So actually you don't average by considering all points having the same weight, but you give some weight, and these weights are here. And of course, in the limit, don't forget that this one here, this width here, is pi over omega, which means in the limit, when omega tends to infinity, you will have from this what? Dirac, and you have your infinite resolution image. But for limited bandwidth, you average out. In the imaging community, this thing here is called point spread function. Why it is point spread function? Because really, if you have a point source, if G is Dirac, and you try to retrieve this Dirac by the limited bandwidth measurements, you convolve this one with Dirac. If you convolve something with Dirac, what do you get? The same thing. So therefore, it is called point. Point spread function means this is G hat produced by a point source, by just one sun. So very, very tiny sun, very, very bright point. So you will have this. Okay? So let us now, before we come to the end, discuss some issues related to the again, a measure of the spread. This is point spread because it's spread out. A measure is pi over omega. If you don't forget that omega itself is twice pi bandwidth, because omega is a circular frequency. So we have, if we let omega is twice pi b, we have the resolution, which, so a measure of the resolution is pi over twice pi b. It is again 1 over twice b. It's exactly like the discrete case, which we considered before. So we have, again, as a rule of thumb, the wider the frequency you can measure over, the more resolution you can get. Okay? In the optical imaging, point spread function is usually, because we are still dealing now with one-dimensional. In optics, the point spread function is a two-dimensional function. You may have, if you have so you measure now instead of time and frequency. In optical imaging, you deal with x and kx, y and ky. So in this case, you will have a very, very similar result, but with the point spread function being in the kx, ky, because here, or in xy, it is something like two-dimensional sink. So some peak and surrounded by minor lobes. Also in the optical, they usually use circular aperture. And in this case, you may approximate this with a Gauss, something like Gauss. And you can always consider now, if you go two-dimensionally, as if this Gauss is a magnifying lens in your hand, and you go through the picture and you average out. What is the impact of averaging out? Let me now simplify a little bit. I will not use the sink. Let us just assume that your point spread function is a rectangular pulse, because not necessarily must be a rectangular pulse, but just to explain to you how the artifacts, now we will talk about the artifacts, how the artifacts can take place. The first effect of artifacts, imagine that you have a point source. A point source should appear to you as G hat as just a point. But now imagine what will happen if you have a point source and you take this sink function as a flag and you go along it. So it will cause a maximum here, or a small maximum, another one here, another one here. So instead of seeing a sun in the picture, you will see 3 or 5 or 7 suns. One is very bright, and 2 less bright, 2 less, and so on. This is one of the artifacts I was talking about. So because of convolving with the point spread function, depending on the point spread function, you may see artifacts. they don't belong to the picture, to the image. But if you understand it in the one-dimensional case, I will generalize this in the two-dimensional. You can understand it also. In the two-dimensional case, as if you have, instead of having a very point source is a very bright point. So instead of having single point, you see it many times and weakened. Now let us go back to what you learned in signal processing. You spent long time in the signal processing talking about windowing. Do you still remember? Windowing the data. So you say, okay, if I take rectangular window, I take the data as they are. I have a ratio between the main lobe and the first side lobe of 13.6 dB. I think it was 13.6. And now, so you read once in a book, use triangular window, or raise cosine window, Hamming window, or Hanning window. Now I think you can recognize what does this mean. If you look now to the artifact, because now in the imaging, you can recognize how useful this windowing is. In my case here, the window is rectangular window, right? If I use triangular window, I will widen the main lobe, but I will lower the side lobes. So my sun, which was point, will be a little bit bigger. But the two suns, left and right, will be much more weaker. So sometimes you say, no, this stupid artifact, I don't want to see the sun 3 times. It doesn't matter when I see the sun a little bit bigger. But better than to see it 3 times or 5 times. So triangular window helps us in doing that. This is signal processing. So actually, instead of taking the frequency measurements, look to the definition. You just need to write down, look to this one here. In defining G hat, I will write this with the window. I will put the window here. Okay? Now, based on that, you will have the window here. So this is the window function here. It is a rectangular window. Okay? And if you have a triangular window, it will be put here. Okay? Or raised cosine, or Hamming, or Hanning. Of course, you know Hamming, Hanning, and so on for the discrete case. But what happens in the discrete and the continuous is the same. But as you see here, I will have the advantage of lowering the artifact. I pay with something. So as you see here, as long as I keep the bandwidth, measurement bandwidth, the same, and I would like to improve something, I must pay with something else. So here, in order to raise the resolution, you may increase this one here. Of course, the suns will come nearer and nearer to each other. Okay, but if you say no, this is resource, this is costly, this is expensive, I would like to keep the same resolution, the same bandwidth, and get rid of the artifact. So they tell you, okay, make windowing, window your data. You will have a bigger sun and weaker side suns. Okay? So this is the first time we talk about artifacts. So artifacts is well explained in terms of the sinc function and this sun story. Okay, let me now deal with the last impact or effect of this convolution. Imagine that our point spread function, for simplicity, it is a rectangular function. So I have something like that. So this is T dash. And imagine that your picture or your image, the infinite resolution image, has an abrupt change. You have white and black. say this is black, and this is white. And now you convolve. So as long as this pulse here is in the white range, you see white. Okay? If it comes here, you still see white. Imagine now that it goes here, because you slide. It starts to be a mix between white and black. And this will continue until it comes here. So continue over this one here. Continue over double the width of the point spread function. Look, you start when it is here. And so in other words, you will have the black-white, something like that. So you will have a gray range between white and black. And the width of this range, it's called blurring. So it is smeared out. This range is again proportional to the spread of the point spread function, which is inversely proportional to the measurement bandwidth. The higher the bandwidth, you see this contrast from black to white or white to black. You see a range where you have all gray degrees. So this is the second artifact. So we consider today two artifacts: the multiple image, and how can you remedy without paying with the bandwidth by just signal processing. The second artifact is the blurring. Blurring means that things are spread out. So instead of have sharp edge between black and white, you see a very small range, depending on the bandwidth, small range when you go gradually from black to white through gray. It's exactly 4 o'clock, and I'm done today. Thank you very much.